But I won September 16th. Oh my god, another hard question. Alright. Alright. Let's deal with this. Shortest path visit. I don't think this is that hard because. Oh no, it is hard. Oh. I just said I don't think it's that hard. Alright. Undirected graph. Connected graph. Undirected connected graph. N nodes. You're given an array graph where graph I is a list of all the nodes connected with node I. Oh, so they give you the graph already. Return the length of the shortest path that visits every node. You may start and stop at any node. You may visit nodes multiple times, and you may reuse edges. Jesus. It must be one of those graph algorithms. I don't know. That's the thing about graph. Okay? That is the thing about graph. At least for me. Any other question, you can always figure something out, right? If you don't know, you just, you figure something out. With graph, it's like, if you don't know the algorithm, you're just done. There's nothing you can do unless you do brute force, all right? What do you think? How do you think this one can be done? Well, n equals to 12. There's only 12 nodes. It's a connected graph, so what we want to do, is it a minimum spanning tree? I mean, we can find a minimum spanning tree. I mean, the minimum spanning tree is but minimum spanning tree doesn't guarantee. Like, minimum spanning tree of this will just be this, right? But the actual path will take a little bit longer, right? It'll take a little bit longer. Think about it. What's the that Eulerian circuit, or Eulerian path? It's a Eulerian path, right? We try to. No, that one is try to go through every edge, right? You go through every edge exactly once. This is to find the shortest path, which means the shortest number of edges to cover, such that you can go through all the nodes, right? That's. It's not Eulerian. No, it's not. I'm trying to, because that's what we learn. We learn Eulerian path, then we learn the minimum spanning tree. But in this case, it can be a minimum spanning tree, but minimum spanning tree, it's just not really minimum. We just need to find a spanning tree. All right, we just need to find a spanning tree. But even if you find a spanning tree, how do you find a spanning tree though? Not a minimum. Well, I guess you just pick one, and now you just keep going. Try to connect everything. Right? It's a path. Right? You want to find a path. Can we brute force it? Maybe we can brute force it. I don't know. Just guessing. I mean, I don't know the algorithm, so we just brute force. We tried all and then see which one gave me the smallest. But which node you start with? That is a question. Which node do you start with? Well, I can say you start with the one that with the least number of degrees. Like if you have one starting with like 1 degree, that has to be the starting point. Because if you don't, you start from something else. Because you'll go there as the last. Alright? And if you go that as last, it's the same as you go that with the start. Otherwise, you have to go there and coming back. Alright, so you're wasting your thing. What if the graph, like, I don't know, just have 4 nodes like that? Which one you pick? Yeah, Jimbo had a good catch. Like, which one do you pick? Like they are, I guess you just pick anyone. Like if we have this. But that's actually a good test case. Alright, where do you start? Now you start here is actually wrong because 1, 2, 3. You can't. It has started here. 1, 2, 3. Okay, so it doesn't feel right. Let's see his hint. Oh my gosh, no hint. DP. Bit manipulation. Bit manipulation. 12, right? BFS. What do you think? I don't know. Well, if we go DP route, we want to find the length of the shortest path, right? The length of the shortest path. I don't know. I mean, we can say if we want to find the shortest path starting from a certain node, okay? Let's say we started from this node. We want to find the shortest path starting from this node. Then we can say, what is the shortest path starting from its neighbor from this node, right? Once we find it, and then we add it to it. And we can say, yeah, that's when we start from here with this one taken. So, like in this case, we have 1, 2, 3, 4, 5, right? So basically, if you do bit 5, 1, 2, 3, 4, right? So it's 0, 1, 2, 3, 4. I say if I starting from, so it's we can say starting position. That's the starting position. We try to find the shortest path, right? And we say starting from here, right? And then we try to find some, and then we add this, right? And then we can say starting from here, or actually not starting from here, just given this state, this is the current state, right? What we want to find is given this state, what is the shortest path, right? We don't know. Now we say, okay, how about we given this state, right? Given this state, and we're going to try to find what, right? And then if we're given this state, we want to try to find, then we can say, okay, how about we do given this state. So eventually what we're going to go through is all these states and try to find the best. That's interesting, right? That is interesting. The end case is like, in this case, it's 1 1 1 1 1. This is 0 because everybody is visited. So right, it takes 0, and then yeah, maybe it's fine, right? But what if I start from here? I say start from this node. So our starting position is 0 1 0 0 0, right? We're starting from this position, okay? Then we need to find. Oh, then we need to find. It's not that straightforward. Maybe it's not DFS, right? It says BFS. Maybe we need to go BFS. How do you go BFS though? Because you need to find like a full path. Well, if we start from here, yeah, how do you solve that? Yeah, given this state, this one is visited. What is the minimum number of? We shall be able to solve it, right? How do you solve this? Like if I say this one's visited, okay? This one's visited, and we are in this, right? Then we want to find is the minimum, the length of the shortest path to visit everybody else, starting from this, right? Starting from this, we want to know. So it has to be not only the state, but also the starting position. Right, so we have the starting position, then we have the state. Then we need to find, okay? Then for this, we say go this way, right? Go this way. So we have the state. Then we say we start from here. What is the shortest path to visit everybody? Or we go here, we say, okay, what is the shortest way to visit everybody? Doesn't sound right, huh? Doesn't sound right. Because you can revisit. That's the thing. The state, it's a bit difficult to say because you can revisit. Maybe, no, because edge you can revisit, nodes you can revisit. Everything can be revisited. All that's required is to visit every node. So what is the state? Right? If you want a DP, you need a state. I have no idea. I give up. Have any explanation? Last node, target node, returns the shortest path from the state where no node is visited to the target state where last node is the last one visited in order to reach target state. No, I mean read it again. DFS, right? So it's DFS. But we have a last node and target state. Returns the shortest path from the state where no node is visited to the target state where a last node is the last one visited in order to reach target. Okay, so we have a target state and we have the last node. This way, all the neighbors of last node are the second last node. There are two possibilities for the target state of last node's neighbor. Either the last node has not been visited when the neighbor is visited. This means the current visit to the last node is the first time the last node is visited, or last node has already been visited when the neighbor is visited. This means the step from the neighbor to the last node is a return trip. Then the shortest path to reach target state with last node being the last node is the minimum of the two situations for each of last node's neighbor. Wait, hold on. So we say the last node is the last node need to visit to reach the target state. And then what we want to say is, given this last node and given the target state, right? We have the last node and then we have the target state. We have the last node and we have the target. So we say anyone has to be the last node, right? So we say for this last node to reach the target state. Hold on, what is the other? I had two solutions. What's this one? BFS. Yeah, this one looks much easier. The neighbor has been visited before. Restrictions on the tuple. Current state. If current state has been seen before, we don't visit again. Current and state. What's the state? Huh? All right, we're not gonna do the DP. DP is just way too complicated. What does this BFS mean? The BFS says so the goal is to reach a node, because when you do BFS, right, you are searching all different routes. You go out, you search the next, you go to the next, you go to the next. So we are taking, and then you can go back, right? You can go back. So I think what the BFS means is, okay, let's just scratch everything, start from the beginning, right? We are trying to find the minimum, the shortest path. Shortest path is BFS, most likely. It's BFS, right? And it says, so basically BFS, we need to visit all the nodes. But it doesn't say which node is the starting point. So every node can be the starting point, right? Every node can be the starting point. Every node can be the starting point. So each node starting point. And then because when you do BFS, you can revisit node, right? You can revisit node. So regular BFS, you're starting from a point and you go out, then you cannot revisit the node. That's why you can only start from one point. But now you can start all of them and start and go out. And the goal is to start from one and try to see if you can reach every node. And the first time you can reach every node, that is the shortest path. But we need to prevent it from revisiting. So that's when the state comes in. Whenever a node is visited, right? If I'm visiting a node, I am going to visit a node. So the state is the node we are visiting and the current state, like what has been visited before, right? If we come back to this, that is bad, right? That is bad. So we need to make sure we don't revisit this. So we need a hash map that can do, actually I'm not sure. Oh wow, we can do this. All right, I need I'll do this today. I think I understand this one. Hold on. We need a Java. Not product queue. It's just a hash set with a array as key. Can we do that? Oh, I have another badge. What's set of lists? So like, how can I hash set key tuple as key, hash set key? I don't know. Tuple as key, yeah. Really? Then you can do this. Ah, pair. I mean, in my case, I can convert to string. Yeah, I can convert to string. Which one do you want? Convert to string or create a think maybe we do a class. Yeah, maybe we just create a class. I've never done this before. Let's try. So you say we do a class tuple int v1 int v2, right? And then we say tuple v1 int v1 int v2, this dot v1 equal to v1, this dot v2 equal to v2. Now you're telling me that this one I can use as the hash. I can use this as hash map. Okay, let's try. Well, what do we call it? Scene hash set. Right, set tuple. Wow, I can't really do that. Scene visited. New hash set. Right, so this is store states that have been visited. Then we need a queue. It's not really a queue, it is a queue. Wait, Java has a queue? Yeah, I think I asked this question before. Yeah, I think it does have a queue. So I can say queue tuple, right? Yeah, tuple queue equals new queue. Wow. Wait, hold on. No. New. I don't think that's a queue. New what? Queue. Linked list. My bad. It's a new linked list. Alright, now we need to put everybody in it. Right, for int I equal to 0. I smaller than graph dot length I plus plus. And so okay, this is node. This is current graph state of which nodes have been visited. Have been visited. What if someone has been visited multiple times? What do you think? Some have been visited multiple times. I guess it's fine. Because if someone has been visited multiple times, like if a node has everything else is the same, and you visit this one 2 times, and next time you visit 3 times, you're always going to be worse than the 2 times, so it's fine. The first time you reach a certain state, that's the most important, right? That's the most. That basically just means you are hitting here, and this one has already been hit before. It doesn't really matter. So yeah, okay. So we're gonna say q dot add, right, new tuple. I think not only that, but your visitor has to add as well. V1 is node. Node is I. State is 1 left shift I. Is that right? 1 left shift 0 is, yeah, 1 left shift I. Then visited add, right? Because these are visited. Because I like when I do BFS, right? I like to put things in beforehand. Okay, beforehand. All right, now we can do BFS. We need to say int res equal to 0. That's the total number of steps. And I say while q dot is empty, not empty, we will get oh. we also need to know the level. Dirt. 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 Alright, we need one more. Alright, we need to change these values. Node, state, and steps. Okay, so node. I don't know why I say v1, v2 steps. Okay, so this is going to be node, and these two is going to be state, right? And this dot steps equals steps. Okay, and then blah blah. Yeah, it's not a tuple, it's a triple. That's fine. Let's not call it tuple. Let's call it node. I just call it node. It's fine. Okay, so now what we're gonna do is this is the node, this is the state, and this is the steps, right? This is the steps. So now I don't need this. Okay, then whenever something come out, we can say node. Inside is node. Call it something else. Node. I don't know what to call it. All right, don't call this node. Yeah, I think this is one you're struggling. You're always trying to. Let's call it index. You happy? Huh? You're happy? This is index. This one is call it index. Index of the node in graph. How about that? Node in graph. Okay, so we have now this has to be node equal to q EUE dot remove offer. What do I do? Which one? Add. Removed at the front. Add to the end. Peak at the front. So it's a remove. Okay, so remove at the front. When I remove at the front, we need to see who else I can go for, right? Who else I can go for. Right, we need to see who I can go for. So we can say for a int next index of graph node dot index. Right? This is the next one. Then we need to see if the state has been visited before. How do we know that? Then we say if, silly me, this doesn't contain. Oh my god, this does not contain. I don't know what you're doing, man. I have no idea what you're doing. It's different. All right, it's different. The Q has to add. Oh, God. It's a different thing. The Q needs to add another. Oh my lord. Hold on. So visited is node. Q is not node. Jesus. Q is int. So Q will be different. Oh my. It's different. Yeah. I know. New int. Shut up. I know. This. And visited is this. Visited is node. Okay? It does not have steps. But Q has steps. My. So int, I would call it temp. That's perfectly fine, right? And we say int next index equal to temp 0. Int I don't know, what's that? State equals temp1 and int steps equal to temp2. Is there a better way for Java to deconstruct? Java extract from array. I don't think that's deconstruct array or I don't know. What's this? I don't think that's the one. What's that? Expand array. Is that what? I don't think it's expand. Extract. Forget about it. That's not necessary to spend time on that. Anyway, where are we? So we are here. Get a temp. We got those three. Then we say, this I can just call it, right? Call it index. Now we have the next index. So we need to say, okay, we need to say if visited dot contains new. Oh, now I can call it tuple. Yeah, now you can call it tuple. New tuple index and state. Need to get a new state. New state shall equal to state or one left shift I. I'm pretty sure. No, it's not I. Next index. Wait, hold on. Is that a state? Yeah, the state is I'm going to, right? This is saying I'm coming to what is the state? Is I get that as a state or before I visit as a state? Yeah, and then this shall be 0 because I'm not coming to this yet, right? This is 0. This is 0, right? I'm going to, yeah, this is the state you're given to me. I'm coming to this state. That is the overall state. So when we get this, we got the state shall be, this is the current state, right? Current state. Index state shall be this or one left shift index. Right? This is when I landed it. Right? I land on this. And the steps is the previous step. Oh my god, is it the previous or the next? I mean, let me think. I think it doesn't really matter, right? It doesn't really matter. I can say it's just I'm going to this node with this state and this number of steps, right? So when I go to that, I need to get my current state and the current number of steps, and I go to the next one. So steps, so this plus 1. Because I'm going to you, need to plus 1 steps. I'm going to this state. So that's the current state, is the current steps, right? This is that. And then we'll go to the next one, right? Go to the next one. So I don't need this. What I do need is to check with state, right? If it contains, then I don't do. But if it does not contain the state, then I can do. Then I say q dot add new int next index state and the steps. I already handled everything, right? I'll go to the next step. And then we blah blah blah. So when do we end? Whenever I have visited all of the nodes. How do you know you have visited all the nodes? Well, I know because when I go to, right, I go to the next one. When I go to the next one, I need to see the state. If the state is equal to, so we should say the end, right? Int end shall equal to 1 left shift graph dot end dot length, the whole thing, minus 1. This is the end. This is the end. So when do I compare it? I say current, I visit this is the current state. Then I go visit the next one, right? And after I visit it, it becomes, which means if state is equal to the end, that's when I break. That's when I break. Which means I need to get the steps on the outside. Get the steps on the outside, so I don't have to redo all this, right? I can say int index, int state, int steps. Get on the outside, so inside I don't have to reinitialize all these things. Okay, I don't have to reinitialize. I got a 3, get an index, current one, go through all of them. So whenever state is equal to the end, we'll get out and we'll return steps. And I initialize it to 0. Step is 0. Beautiful. Right? Step is 0. If I have only one node, step should be 0. What do you think? Let's give this a shot. Make sense? Nope. Output 5, expected 4. Interesting. Did you mess up with a step? Maybe. Let me think again. This is, I added this and I add a step, right? Is this the previous one? Then I go to the end. Hold on, let me think. We start from nothing, right? We start from nothing. And then we go to this. So when I landed this, I add a 1. Okay? And then I landed at a 2. And this is 3. And then this is 4. Right? I landed this as 4. And that state. Shouldn't this be right? Hold on. Yeah, it's very frustrating.
Leave these here.
Yeah, leave this here. Okay. Graph Yeah, I need to figure out what went wrong. Time to eat.
Which one?
Ah, I'm coming. Alright, I'll be back.
I think
It's this one.
I'm trying to figure out the back, please.
Yes. It's my current state, right? Current is nothing. This. And current state is nothing. Then we go to the next one. Current state is nothing, right? Whatever the current state is. Then I'll go to this. Okay? So I go to it. And we got a new state. Right, we got a new state. I add a step. Then I check the next I want to go. The next one. Okay? Check the next one.
Yeah.
Then I will go to the next one. Go to the next one. And once I finish this next one, and it shows up that I have visited everything, then I show that you'll be. I don't know. I don't know what went wrong. Alright, I debugged this. Interesting. I wanna know. Oh, I need to put a. You need to put a. Let's put the stop here. I'm telling you, debugging is very interesting. Okay, so what do we have? 0, 0, 0, right? 0, 0, 0. Oh my god, this is gonna take a long time to go through. It doesn't take a long time to go through. State is 1, step is 1. No. 0 only have 1. So we add 1. 1, 1. Nothing. Get out. Next one is 1, 0, 0. Okay. Next index. Oh, I think I'm typo. I think it's a typo. That's not index. This is the next index. Yeah, I think it's the next index. Oof. Still 5. Oh, it's definitely a typo. Maybe I need to tell it how to hash it. Yeah, you have to use hash. I didn't have hash, so it doesn't really work. How to override hash, right? Override equals. Oh, override. Ah, I remember. What question is this? Yeah, I remember you have to do both. Objects.hash. Oh, yeah, I have to use that. Alright, let's hash. My god.
I have a complicated role tomorrow.
Really? Well, as a challenge, I need to override some stuff. So public hash code. So I saw the other solution has object.hash. On each pass, to collect each result, calculate a hash on the collected results. This is what we need. Dot hash. Objects. dot hash index state, right? And I'm pretty sure we need to override. Oh, did I write it wrong? Does not override method from its superclass. Extract. Wait, hold on. What does that mean? Extract to new interfaces. Wait, what? Override. So do I have to say this? What does it mean? How do I override? Oh, is it override or overwrite? Override, yeah, it's override. Override hash code. Class, blah blah blah. Public boolean. Yeah, it has override. Why I cannot do override? What did I do wrong? Oh, hash. My God. Override public equal. Is it int equal, right? Oh, boolean equal. Boolean equal. Why we have to override both? Hash code is to get, but if you don't override equals, you don't know which one is equal to. Wait, hold on. I remember there's a answer. Why override equals and hash? Yeah. Or only equals. If only equals overwritten, then when you call, they'll put. So a hash to some bucket, when you call, it'll hash to some other buckets. So you have different hash code. Because your hash code is different. So although they are equal, and they don't hash to the same bucket, and both of them stay in the map. Yeah, because your hash code and your equals have different behaviors. Only override hash code. If you only override, then we will call. Takes first, calculate the hash code and store it. And when you call map.put, it should replace first with second because they're equal. But the problem is that equals was not redefined. So when the map hashes second and iterates through the bucket, look for if there is an object such that it won't find any. Be false. You need to override a hash code if your class are equal, but reverse is not true. That's how I would imagine, right? You should only override hash code. Uses hash code value of object to determine how it should be stored. And hash code is used again in order to locate the object. Hashing retrieval is a two-step procedure. Find the right bucket, search the bucket for the right element, use equals. Find the right bucket. Find the right bucket. Hash code is to find a bucket. And then use equals. The equals compared what? Your object, right? It compares your object. Oh my god. So this will do this. Well, I mean, this doesn't have a hash code. The hash code is different. Now the hash code is the same. Yeah, they can consider equal, but the hash code is different. That's a good question. I think the best is just to do them both, because then we can make sure everything will be fine. And then this one is actually a bit complicated, so it's going to be an object other, right? And we say, I think the first you have to check if it's okay. So if this is equal to other, we'll return true, right? And if other is equal to no, get class. Avoid doing that. If it is of type geek by comparing the classes of the past argument. Or other dot get class is not equal to this dot get class. That makes sense. That will return false. Right? Now we need to cast it. Tuple O equal to tuple other, right? Then compare is equal, so return O dot index is equal to this dot index. Yeah, I think using this is a good idea to make it sure which one is which. And it has to be and O dot state equals this dot state. Right? I think that's hold on. That's fine. We both are integers, so we don't need to call equals. Hash, we do this hash. So now with this, oh god, and it's still wrong. You gotta be kidding me, man. Yeah, it's not gonna be the hash issue because we already fixed the hash issue. It's just the code. Something is not right. I'm still getting 5. Why? Can I always see the Q? Right? Times 0, 0, 0. We have a 1, so Q will add a 1, 1, 1. Right, we have one step. I have 1. Next is 1, 0, 0. Okay. Index is 1. State is 2. And we try to see that. Yeah, we'll go there. Oh, I have 3 things to go. Yep. Okay, so now Q, right? First is index, so we shall keep track on the 4. So I keep going. Did a 4 come up? Almost. No, that shall be... One, 1, 1. Yeah, there's a 1, 1, 1. 1, 1, 1. If I can show... See, this is the thing that I don't like. I think debugging might be a little bit... Let's print it out. Let's print out every single time that we hit. This is the current one. Hit, here. I think we want to print out this. So we say system.out.print line. Index. How do I print line formatted to print? String, no, formatted string. Ah, okay. String.format. So %d, %s, %d. Oh, I want convert int to binary string. To binary string. Okay, so the index state, no, integer dot to binary string state, and then steps. There we go. All right, so let's see what's gonna happen. Huh? Hold on. Java, I'm in trouble. All right, I'm back. Why it give me error again? What did I do wrong? Redundant, too many arguments. Found 3, expected 2. Oh, Jesus, man. Oh no, I don't want. Alright, now we can kind of inspect. Now can we left pad? Do we have a left pad? No way. You gotta be kidding me. Yep, I guess that's it. 16, right? Okay, so we're gonna have the string formatted. Jesus. So instead of doing this, we have to do this stupid thing. I don't need 16. I think 5, right? Because the most 0, 1, 2, 0, 1, 2, 3, 4, 5, 6. State. 5. 5 is enough. Interesting. So 0, then we shall go for 1, this 2 step 1 1, then we shall go to 4. 3 with 4, yeah, and then 2 shall, oh, we need a -1. Silly me. That's not steps. Nodes. Num nodes. Or we call it -1 at the beginning. Okay. What? We go steps. Oh, it's not steps minus 1. Shoot. It's here when we start. Minus 1. Plus, we don't print out anymore. Come on. Yeah, steps really, I don't really care about steps. Okay, I think next is right by itself. Hmm. 0. Okay, I can write something for this. Yeah, we failed this one. Well, we've been having a series of failures. This is a new one. I had to check my previous solution. Now the DP one is extremely complicated. And I don't like it. This BFS is very simple. It's akin to how we usually do BFS to find the shortest path. The only difference is that in the current case, we are allowed to revisit a previously visited node. However, the spirit is the same. We BFS do not repeat a previously conducted step, and the first time we have visited all the nodes is the shortest path. Now the question is, how do we determine a previously conducted step? Well, the answer is, if we have a state, right, of all the nodes that have been visited and the current node to visit, these two combined can serve as the key, right, for a conducted step. Thus, we use a tuple class to represent this, to represent each step, right? And we make sure the same step is not conducted again. Since the total number of nodes is only 12, a bit mask is sufficient to represent the state of visited nodes. One last thing to note is that the number of steps is 1 less than the number nodes visited. I don't even know what is the runtime. Let's just get this one going. Okay. Ooh. Something is not right. Whoa. 40. 51. Alright, something is not right. What did I do wrong? Interesting. The hell? Yeah, I know. Let's see. What is BFS? Oh, shoot. Just forgot to visit. My bad. I forgot. Unbelievable. Forgot to visit part. So many typo. What? It's terrible. Runtime is terrible. Because of this, I guess. Can we not write this? Just try. No, you cannot. Right, you have to do this. No, you have to do both. Interesting. String. String. This is slow. Let's try a string. String dot format. We say, yeah, 0 and 0. Right? I and 0. With a string. So we don't do this. And string next shall equal to dot format percent D, percent D. Is it correct here? Yep. Damn, we don't have to bother with another class. This one, right? Yep. Oh, 21. Oh my god, it's even slower. What the hell? No, this is slower. I don't know. Alright, anyway, it's late, so I'm gonna end it here, but I need to check why this one's slower. Alright, I'll see you guys tomorrow.